We are given that the angular velocity of a flywheel is 200 revolutions per minute, and part A of this example problem asks us to convert that angular velocity to radians per second. So I could say omega is equal to 200 revolutions per minute. This basically means that the flywheel spins around 200 times every minute, so it is spinning pretty fast. Now, to convert revolutions per minute to radians per second, we need to do two conversions. We need to convert revolutions into radians, and we need to convert minutes into seconds. So I could say one revolution, one complete spin around the circle, is 2 pi radians. Because revolutions is upstairs, I will put revolutions downstairs when I do my conversion. So 2 pi radians over 1 revolution. Because minutes is downstairs in this unit, I will put minutes upstairs when I do my conversion. So I have 1 minute over 60 seconds. And when I cancel out the units, minutes cancel with minutes, revolutions cancel with revolutions, I'm left with an angular velocity of 21 radians per second. In part B of this problem, we are asked to find the linear speed of a point on the edge of the wheel. We're given the radius of the wheel. The radius of the wheel is 0.6 meters. So here is the wheel. It is spinning around at a rate of omega equals 21 radians per second. And we are asked to find what is the speed of a point on the edge of the wheel. The wheel has a radius of 0.6 meters, so I could use V equals R omega. With V equals R omega, I could say the speed of the point on the edge of the wheel is given as 0.6 times omega, 21. And when I put that in a calculator, I find the speed of a point on the edge of a wheel is 12.6 meters per second. We found that right now the wheel is spinning at a rate of 21 radians per second, but we want the wheel to spin up faster. We want the wheel to reach an angular velocity of 1,000 revolutions per minute in 60 seconds. Because this is the current angular velocity of the wheel, I'm going to call this omega initial. What we want is omega final to be equal to 1,000 revolutions per minute. In order to solve this problem, I'm going to convert this 1,000 revolutions per minute to radians per second, and I'm going to do it just like I did in part A. So I could write omega final, we want to be 1,000 revolutions per minute, and 1 revolution is 2 pi radians. I could do that conversion, 2 pi radians over 1 revolution, times 1 minute over 60 seconds. And when I do this conversion, I find that the final angular velocity of the wheel is going to be equal to 104.7 radians per second. Now, at what constant tangential acceleration will the wheel achieve this final angular velocity in 60 seconds? So ultimately, what we want to find is the tangential acceleration. Well, it's not immediately clear how we will find this, so let's see if there's something else we could find, and maybe we could relate that other quantity to the tangential acceleration. Let's try to find the angular acceleration first. If I look for the angular acceleration, I could say, well, I have an omega final, I have an omega initial, and we want the wheel to achieve its final angular velocity in 60 seconds. So I could say omega final equals omega initial plus alpha t. And so omega final is going to be 104.7. Omega initial, the initial rate at which the wheel is spinning, is 21. And angular acceleration times t here is going to be 60 seconds. When I solve for the angular acceleration of this problem, I find that the angular acceleration alpha is 1.4 radians per second squared. Will knowing the angular acceleration help me find the tangential acceleration of the wheel? Yes, it will, because angular acceleration is related to tangential acceleration. They're related by tangential acceleration is equal to r times alpha, and we know the radius of the wheel. We could write tangential acceleration is equal to 0.6 times 1.4, and if I put these numbers in a calculator, I find that the tangential acceleration of the wheel to achieve this final angular velocity is going to be 0.84 meters per second squared. In this example problem, we have two wheels that are connected by a belt. Wheel A is the smaller wheel with a radius of 10 centimeters, and wheel B is a larger wheel of a radius of 25 centimeters. I already converted the radii of these wheels to 0.1 meter and 0.25 meter because we always want to work in units of radians, meters, seconds, and kilograms where appropriate. Wheel A is initially not spinning, it is initially stationary, so I could write wheel A's initial angular velocity as 0, but wheel A is going to begin spinning up faster and faster with a constant angular acceleration of 1.6 radians per second square. And the question is, how long, how many seconds will it take wheel B to reach an angular velocity of 100 revolutions per minute? So essentially that is saying this is the initial angular velocity of wheel A. We want this to be the final angular velocity of wheel B. How long will it take? Well, because wheel A's angular velocity is written in radians per second here, let's convert this to radians per second as well. So I could say the final angular velocity of wheel B is 100 revolutions per minute. But I'm going to convert this, so I will multiply this by 2 pi radians over 1 revolution, and I'll multiply this by 1 minute over 60 seconds. And when I perform this calculation, the minutes cancel, the revolutions cancel, I get the final angular velocity of wheel B is 10.5 radians per second. Now, before we proceed in this problem, let's think about what's going on. We have a whole bunch of different quantities in this chapter we could consider. We could consider angle theta, angular velocity omega, angular acceleration, linear velocity. Think about the different quantities in this chapter and ask yourself, what quantity will allow us to connect what is happening to wheel A to what is happening to wheel B? In other words, there must be a quantity that is identical for both wheel A and wheel B. Pause the video, think about it, come back with an answer. The quantity that is going to allow us to connect what is happening to wheel A to what is happening to wheel B is going to be the linear velocity of a point on the edge of the wheels. To justify that claim, let's think about what's happening to the wheels. The wheels are connected by a belt, and let's imagine there's a small insect riding on the belt. So maybe there's an insect right here riding on the belt. But this is a fun ride, so the insect calls some of his friends, and there might be another insect over here on the belt, and there might be another insect over here on the belt, and there might be an insect over here on the belt, and over here. Now, if you think about what's going on in this scenario, the belt connects the two wheels, and the speed of this insect should be the same as the speed of every other insect on the belt, because the belt is not getting stretched apart or scrunched together. The belt is going to have the same speed everywhere along it. So I could articulate that idea by saying the speed of this insect that is riding along the edge of wheel A is going to be the same as the speed of this insect that is riding currently right along the edge of wheel B. So I could say the linear velocity of a point on the outer edge of wheel A should be equal to the linear velocity of a point on the outer edge of wheel B. And this will be the key to connecting what is happening to wheel A to what is happening to wheel B. Now, we learned that V equals R omega. So for wheel A, I could say RA omega A should be equal to the linear velocity of wheel B. The linear velocity of wheel B could be rewritten as RB omega B. So if I wanted to, I could write the linear velocity of wheel A, omega A, as RB over RA times omega B. So now we could rephrase this question as asking, how long will it take wheel A to reach a final angular velocity given by this if it is to have a constant angular acceleration of this much? So the final angular velocity of wheel A that we want to find is omega A is equal to the radius of wheel B is 0.25 meter, the radius of wheel A is 0.10 meter, and the final angular velocity of wheel B that we want is 10.5. So I want the final angular velocity of wheel A to be 26.25 radians per second. Omega A equals 26.25 radians per second. Now this question has become fairly straightforward. What we are asking is, we said omega initial for wheel A is equal to 0, omega final for wheel A is equal to 26.25 radians per second. We know the angular acceleration of wheel A, that is alpha A, is equal to 1.6 radians per second squared, and we are asked to find how long it will take wheel A to reach this final angular velocity. To determine this time, I will write the final angular velocity of wheel A is equal to the initial angular velocity of wheel A plus the angular acceleration of wheel A times time. To convince yourself that the angular velocity of wheel A does not need to be equal to the angular velocity of wheel B, imagine wheel A is really teeny tiny and wheel B is huge. In order for the belt to advance 1 centimeter on a really tiny wheel, wheel A will need to spin a lot. And in order for the belt to advance just 1 centimeter, if wheel B is enormous, wheel B will barely spin at all. The amount of spin of these wheels does not need to be the same, but the speed of the belt, the amount the belt moves, should be the same at every point along the belt. So wheel A, the final angular velocity is 26.25 radians per second. The initial angular velocity of wheel A we set to be 0. The angular acceleration of wheel A we set to be 1.6, and we're trying to find the time it takes wheel A to achieve this angular velocity. And if I put these numbers in a calculator, I find the time it takes wheel A to achieve this final angular velocity, which is the same as saying how long does it take wheel B to achieve an angular velocity of 10.5 radians per second, is 16.4 seconds.